Hey everyone, and welcome to this explainer. I am absolutely thrilled you're tuning in today because we're going to dive into one of the most foundational and honestly coolest chapters in all of math. If the word trigonometry usually makes you want to run for the hills, do not worry. We're going to break this whole thing down conceptually, step by step. So let's just jump right in. Okay, I want you to picture this. You're standing right in front of a massive, incredibly ancient monument. Naturally, you want to know exactly how tall it is. But here's the catch. You obviously don't have a giant tape measure on you, and climbing it? Yeah, that's not happening. So how on earth do you measure something you literally cannot reach? This isn't just a fun little riddle, It's a real-world problem humans have been tackling for thousands of years. Well, the secret actually lies in simple geometry. Let's say you're looking at the Qutb Minar. If you stand on the ground and look straight up to the very top, your line of sight, the monument's height, and the ground between you two actually form a shape. It's an invisible right triangle. By cracking the math of that invisible triangle, you can figure out the exact height without ever touching a ruler. It's basically a mathematical superpower, and that's exactly what we're unpacking today. So here's our quick roadmap for today. First, measuring the unreachable. Second, origins of trigonometry. Third, the 6 trigonometric ratios. Fourth, size does not matter. And finally, ratios for specific angles. Let's kick things off with section 1, measuring the unreachable, real-world math. Now, the Qutb Minar is definitely not the only place these invisible right triangles pop up. They are literally all around us. Imagine a girl hanging out on her balcony, looking down at a flower pot across a river. If she knows how high up her balcony is, she can use that invisible right triangle to calculate the exact width of the river. Or think about a hot air balloon drifting across the sky. As it moves from point A to point B, it creates new right triangles that let us calculate its precise altitude. Ancient astronomers actually used this exact same trick to figure out the distances of stars and planets from Earth. Crazy, right? Moving right along to section 2, origins of trigonometry, a global human effort. Before we even look at a single number, let's talk about the word itself. Trigonometry sounds super heavy and academic, but it's really just a mashup of 3 basic Greek words. Tri means 3, gon means sides, and metron means measure. That is literally it, the measurement of 3-sided shapes. At its core, the whole field is just studying the relationship between a triangle's sides and its angles. And figuring all this out, it definitely wasn't a solo job done in an afternoon. No way. This was a massive, centuries-long global effort. The earliest recorded works go way back to ancient Egypt and Babylon. Then, around the year 500 CE, the brilliant Indian mathematician Aryabhata introduced the conceptual use of sine in his text, the Aryabhatiam. Fast forward to Europe between 1581 and 1626, and you've got an English astronomy professor named Edmund Gunter originating the term cosinus and using the abbreviation sin. Then, in 1674, Sir Jonas Moore officially gave us the abbreviation cos. Actually, my absolute favorite part of this global collaboration is the journey of the word sine. It's wild. Aryabhata originally used the Sanskrit term ardha for a circle's half chord, which got shortened to jiva. When his work was translated into Arabic, they just kept it as jiva. But here's the funny part. When that Arabic text was later translated into Latin, the translators mistook it for the word for curve or fold, which in Latin is sinus. And eventually, sinus morphed into the English word sine that students all over the world use today. All right, let's get into the mechanics. Section 3, the 6 trigonometric ratios, basically your mathematical toolbox. Whenever we're dealing with an acute angle inside a right triangle, let's just call it angle A, these ratios are literally just fractions. We're just comparing the lengths of 2 different sides. The sine of angle A is the length of the side totally opposite to the angle, divided by the hypotenuse, which is of course the longest side. The cosine is the adjacent side, the one right next to the angle, divided by the hypotenuse. And tangent is just the opposite side, divided by the adjacent side. That's the whole magic trick. They're just fractions showing how the angle and the side lengths relate to each other. Once you have those 3 down, the remaining tools in the toolbox are an absolute breeze. We just covered the primary ratios, sine, cosine, and tangent. The other 3 are called reciprocal ratios, cosecant, secant, and cotangent. And you don't need to memorize any crazy new formulas here because they do exactly what it says on the tin. They're reciprocals. Cosecant is just the sine fraction flipped upside down. Secant is cosine flipped. Cotangent is tangent flipped. Seriously, if you know the first 3, you automatically know all 6.
Which leads us perfectly into section 4, size does not matter. The universal ratios.
Now, this is the part that usually blows people's minds. Our source material puts it perfectly. The values of the trigonometric ratios of an angle do not vary with the lengths of the sides of the triangle if the angle remains the same. Let that sink in for a second. If you have an angle of 30 degrees, it does not matter if your triangle is drawn on a tiny post-it note or if it spans the entire width of our solar system. As long as the angle is exactly the same, the fraction for the sine, cosine, or tangent will be the exact same number.
And we don't just have to take that on blind faith. We can actually prove it using the geometry of similar triangles. Imagine you draw a really small right triangle. Now extend its hypotenuse and its base way out and close it off so you've built a much larger right triangle right on top of the original one. Because they share that same base angle and they both have that 90-degree right angle, we can use the angle-angle or AA similarity criterion. This geometry rule proves those two triangles are mathematically similar, and because they're similar, their corresponding sides grow at the exact same proportional rate. The top of your fraction grows at the exact same rate as the bottom, which means the ratio, your final value, stays flawlessly, constantly the same. Knowing that these ratios are basically universal truths, let's hit our final section. Section 5. Ratios for specific angles. Calculating exact ratios. Let's try figuring out the ratios for a 45-degree angle. And hey, you don't need to go memorize some giant table for this. You can literally just build it in your head. Picture a right triangle where both acute angles are 45 degrees. That makes it an isosceles triangle, meaning two of its sides are exactly equal. Let's call the length of those two sides a. If we use the classic Pythagoras theorem, a squared plus b squared equals c squared, we find the hypotenuse has to be a times the square root of 2. Okay, so what's the sine of 45 degrees? It's opposite over hypotenuse. That's a divided by a root 2. The a's beautifully cancel each other out, and boom, you're left with 1 over the square root of 2. By just picturing that one simple shape, you can grab the sine, cosine, or tangent for 45 degrees whenever you need it. We can do a really similar geometric trick to find the ratios for 30 degrees and 60 degrees. First, imagine an equilateral triangle. All sides are equal. Let's call the length 2a, and all angles are perfect 60 degrees. Now drop a straight perpendicular line right down the middle. You've just sliced it into two identical right triangles. That top angle got cut in half, so now it's 30 degrees. The base got cut in half, so it's just a. If we use Pythagoras on this newly sliced triangle, we find that the straight line we just drew has a height of a root 3. So looking at that 30-degree angle at the top, the opposite side is a, and the hypotenuse is 2a. Sine is opposite over hypotenuse, right? A divided by 2a. The a's cancel out, leaving us with exactly 1/2. It's like magic. We just geometrically crafted the exact ratios for both 30 and 60 degrees out of thin air. And that brings us to the end of this explainer. We've unpacked how simple fractions, just ratios of sides inside a right triangle, turn out to be absolute universal truths, completely regardless of scale. We traced how this mathematical superpower was pieced together across the globe over centuries, from Babylon all the way to Europe. It gave humanity the tools to measure rivers from a balcony, monuments from the ground, and literally the distance to the stars. So I'll leave you with this thought. If trigonometry unlocked the cosmos for ancient astronomers, what modern, unreachable problems are you going to solve with it next? Keep questioning, keep learning, and thank you so much for joining me today.